Hello everyone. Today we will discuss the variation of the acceleration due to gravity with height, that is altitude, with depth and the shape of the earth. So first we will take the variation of acceleration due to gravity with the height. So let's take the earth having mass m, capital M. The radius of the earth I am taking as capital R. So if any object is here, so you can say that this is at the surface is given by g m upon capital R square, because if the object is here, then the separation between the centers will be capital R. Now if we are considering at height h from the earth's surface, if the body is here, then this is the height h, right? And if we consider it, the separation between the centers can be taken as small r. So we can write that the value of acceleration due to gravity at height h will be g capital M upon small r square, and this can also be written as g m upon r plus h whole square. So this is clear from the diagram. Capital R plus h gives you small r. Right? So let's take this as equation 1 and this as equation 2. So we are checking the variation with height. So we'll divide equation 2 by equation 1. What will we get? GH. This is suffix. Don't write it of the same size. Suffix means this is just to denote that this is gravitational acceleration at height h. This is gravitational acceleration at surface, and this will be equal to g m upon r plus h whole square upon g m upon capital R square. From here, g m will be cancelled and you will get, this will go up. So this will be 1 upon r plus h square into r square. If I want to cancel r square, I can take this r square common from the denominator, and inside this will be 1 plus h upon r. Why? We have to take this r outside, and there is a square on this term. So this has to be written in square form if I am taking it common outside. So this way, this part will be cancelled, and if we solve it, we will get GH is equal to GS into 1 plus h upon r to the power minus 2. So this is, let's mark this as equation 3, right? And this equation can be written as 1 minus 2h upon r using binomial theorem. We have studied this binomial theorem in chapter 2 also, but I'll remind you how it is like this. So by binomial theorem, we know that if x is very small, in the expression 1 plus x to the power n, if x is very small, then this can be written as 1 plus nx plus higher powers of x. If x is very small, then higher powers of x will even be more smaller. If we have 0.1, then the square of 0.1 is 0.01, right? So if we take another square, so it will be 0.01 whole square will be 0.0001. So higher powers can be neglected because this will be very, very small. So we can simply write it 1 plus nx. Here if we take this as n, this as x, now this condition is applied because h upon r must be very, very small. So this is the condition when r is very greater than h, then h upon r will be very small. Then we can apply the binomial theorem, and that's why we can write it like this, because here n is equal to -2, x is equal to h upon r. Therefore, g as it is 1 plus h upon r to the power -2 becomes gs as it is, and here 1 plus -2 into h upon r by using this. For x we have h upon r, for n I have -2. So obviously if I have to write 1 plus nx, so I will write n is equal to -2 and x is equal to h upon r. So this gives me this. I hope this is clear. So we have these two formulas for variation with height. So the first formula is, and second formula, I am writing both the formulas. GH is equal to r square upon r plus h whole square when r is comparable to h, right? And GH is equal to this into G at the surface, and second formula is G at surface multiplied by 1 minus 2h upon r, and this is applicable when r is very greater than h. So these are the two formulas which I am placing in the box, right? So this was about the variation of g with altitude. Now let's take it the variation of g with depth. So if we have this as radius of earth, capital M as mass of the earth, then if we take a point at depth d from the surface, right? So this is the center, this is the surface. So if the object is at the surface, what is the value of g at the surface? This will be g m upon r square. This can be written in terms of density. How? M can be written as volume into density. Volume of what? Volume of earth. So this can be written as 4 by 3 pi into radius of earth cube into density of earth upon r square. So this gives me g 4 by 3 pi r rho, right? So this is about the surface because this square will be cancelled here. Now if we are writing about the depth, let me redraw a bigger diagram here. This was capital R. M is the mass of the earth. This is the depth. I am talking about this point. This is the center. So when the body is here at this point, what will be the g at depth? This is what we have to find. So this will be g m dash I will write. Why am I writing this m dash? This is an important point to be considered here, because when we are talking about this point, then the sphere of influence of the material of the sphere which this point makes, this will be applicable, this will be effective in attracting this body. So this mass of this part of the sphere will be m dash upon separation between the two centers. So this body is at this depth, this total is r. So if this total is r and this is d, I have to find this separation. What will it be? R minus d. So I have to write this separation, which is r minus d. I hope you are getting it. So this is r minus d whole square, because this is the separation between the centers of the two bodies. One body is the earth, the other body is here at depth. So this can be written as volume of this part of this square. So this will be volume dash. Density is considered uniform for the earth material, and this is r minus d whole square. Now this can be written as 4 by 3 pi, because we have to find the volume of this part. So its radius is r minus d. This is r minus d whole cube upon r minus d whole square. We can cancel one power. Now this will give me g at depth is g into 4 pi 3 pi r minus d into rho. Let's mark this as equation 5 and this as equation 6. I have to find small g at depth d. So divide 6 by 5. So what will I get? G at depth upon g at surface is equal to g into 4 by 3 pi r minus d into rho upon g at surface is g into 4 by 3 pi r into rho. Let's cancel whatever is possible to be cancelled. So this g, this. So I can write it 1 minus d upon r. Right? From here g at depth will be g at s into 1 minus d upon r. So this gives me the formula for the variation of acceleration due to gravity with depth. So this is important. Now let's discuss with shape. If I am talking about the actual shape of the earth, it's oval. Right? So you can say that the radius at equator is greater than radius at poles. So r at equator is greater than r at poles. We know the formula for acceleration due to gravity. This at equator will be g mass of earth upon radius at equator whole square, and g at pole will be g m upon radius at pole whole square. We know that this is inversely proportional to radius square. So at equator the radius is more, so gravitational acceleration value will be less. So g at equator is less than g at poles. there is an interesting story here. There were two friends. One friend was at equator, the other friend was at poles. This is an imaginary story. So from poles, the friend purchased 1 kg of gold, and then he went back to another friend at the equator. Right? This is the first one. This is the second one. He gave that 1 kg gold to his friend, which he had asked him to bring. So this was not a gift. So when he gave it to him, he weighed it. He weighed it and he found that the value of the gold was less than 1 kg. So he blamed his friend for not bringing the actual amount of gold which he had asked for. But the reason lies here in physics, because G value at equator is less. So the same gold weighed less at the equator. So I hope this is very much clear, the variation of acceleration due to gravity with the height, depth and the shape of the earth. So that's all for now. Have a nice day.